For the first equation of motion, which is this one, the velocity is equal to the initial velocity plus the acceleration times time, we can derive this just by using the acceleration equation. So if we start with acceleration being the change in velocity over the change in time, we can just rewrite this in terms of v final minus v initial. And we can just talk about this in terms of time for now. If we just rearrange this to get initial velocity, we multiply out, we get AT plus VI, and that equals V final. And we can rewrite this in a different notation, and we can write V is equal to V naught plus acceleration times time. So this is the velocity at some point, and it's equal to whatever speed you were moving at plus the acceleration. So how long you accelerated for, added to your initial velocity. So if I was moving along at a constant speed of 5 meters per second, and then for 2 seconds I speed up by a certain amount, 2 meters per second. If it's 2 seconds at 2 meters per second, therefore in that time I would speed up by 4 meters per second. So I add that to my initial velocity. I'm now moving at 9 meters per second as my final velocity. So that is the first equation of motion. For the second equation, we need two things. Firstly, we need the position equation. So very similar to the first situation, if I want to know where I am, I need to know where did I start. So we'll call that S naught. And then I add my motion to it. So if I was moving, I had a velocity, and how long was I moving for? I would have a time. And I could derive this from a different equation. I could derive this from the velocity equation. So if velocity is equal to the distance over the time, for example, now I've put the delta to show it's a change rather than just representing from a zero to a motion and from zero time to some time. But we can write it the same. So if velocity is distance over time, I can rearrange this to say that delta S is velocity times time, which we already know. But if I expand this out, this is S final minus S initial equals V final minus V initial times time. And I only want my final distance. So I can rearrange, move this across, and I get that distance is equal to SI plus velocity times time. And I could write delta there. So that's my average, or just my velocity. Often we use SI for S initial, sometimes we use S naught. So if I just represent this by S naught, I've got what I started with. And that's how we get the first part. So from this, the second thing I need is average velocity. So if I was talking about a delta V back here, how do I find an average? So if I was to write V average, just like in basic maths when I find the average of a number, I would have V plus V naught divided by 2. So if I know I was traveling at this speed here, and I was traveling at this speed here, what's my average? Well, I could do the physics formula, or I can just say, well, if you just want an average, it's this plus this divided by 2, and it'll give me somewhere in the middle. That's your average. So if I substitute this in, if I substitute this average into this equation, it becomes this. I get the distance traveled is equal to the initial position plus, and our velocity average becomes this. So it's V plus V naught over 2 times T. And now I can expand this out a little bit. So I go S naught plus Vt on 2 plus V naught T on 2. But here, I've got a velocity times time, and I've got a V naught times time. From the first equation, we just said that velocity is equal to V naught plus AT. So if I substitute that in, I get my S naught plus this piece, which is the V naught plus AT. That is going to be times by T, and it's going to be divided by 2. and I just get my plain old V naught T over 2 back here. So if I expand this out, the next line becomes my S naught still, plus I get a V naught T over 2, plus now I'm going to have an AT squared over 2, and I've got my V naught T over 2 from before. So I've got a V naught T and a V naught T. I can add those two together, and that gives me 2 lots of V naught T over 2. And then you can see from here that these are going to cancel out. I get my S naught still, and now I get what I can write as a half AT squared. So this is basically saying the distance where you are, where you've travelled to, is equal to where you started, plus your initial velocity times time. So how fast you were moving times by how long you were moving for that speed. Add it to half of the acceleration times the time squared. And the S naught, we could either move across and have an S minus S naught and just change that to a delta, or in a lot of cases we kind of just ignore that. So we often just say it's V naught T plus half AT squared. It doesn't really matter because it's an initial position. We assume the initial position is 0. But if not, you would factor that in. So our second equation becomes distance equals ut plus half AT squared. And that's using u as initial velocity. However, in the sake of keeping it all consistent, we'll rewrite V naught T. So S equals V naught T plus half AT squared is the second equation of motion. For the third equation, we start with what we had from number 1. The velocity is equal to initial velocity plus acceleration times time. If we rearrange this for time, we get V minus V naught over A equals time. And now the second part is, if we want to know the position, not this kind of position, but just a standard motion, we would say, let's say X for a position along an X-axis, for example. The position where you are is equal to where you started plus your motion, the velocity times time. From here, if we substitute this into time and also consider the fact that, like we said before, this velocity is an average velocity because there's no acceleration or anything like that. We're just assuming it's an average. So we would also have that V is equal to V plus V naught over 2 as an average velocity. So we would substitute these into the time and into the velocity. And we would get something that looks like this. We would have our X naught plus V naught over 2 times V minus V naught over A. And if we expand this out using a bit of brackets, the inside-outside lasts the FOIL, we would get V squared minus V naught plus V naught minus V naught squared. And that's all over 2A. We've still got our X naught, and that's equal to just plain old X. So there's a few things I can do here. Firstly, if I break it into individual fractions, I'll have V squared over 2A. I'll also have a minus V naught squared over 2A. And here I'm going to have minus V naught plus V naught, so those vanish. So I've just got this, and I've got X naught equals my original X. Now the last thing I want to do is, if I move this across, I'll get X minus X naught. So X minus X naught equals everything on the right hand side. Well, I'll leave that as V squared over 2A minus V naught squared over 2A. X minus X naught is the same as the distance, right? The change in position is how far you've traveled. So I can write this as S, because it's equal to how far I've traveled, and then all of this stays the same. So if I rewrite this from here, I could skip a couple of steps and say, well, I want velocity squared as the term. I want that to be the main equation out the front. So if I rewrite this, do a few steps, I'm going to rearrange this by moving these across, and because they're both on the denominator, I can times this side, so I get 2 lots of my AS. The 2a comes from here, the s was just the x minus x naught. That's going to equal v squared minus v naught squared. And then I move that across, I'll get v naught squared plus 2as equals v squared. And lastly, I'll just flip this around so that I've actually got the term I want in the front. I get v squared equals v naught squared plus 2as. So the velocity squared that I want, or the final, is equal to the initial velocity squared plus 2 times the acceleration times the distance travelled. So the third equation is v squared equals v naught squared plus 2as. And that is Newton's third equation of motion.